So we've been looking at how magnetic fields have been created. But once you have a field, it can apply a force on particles. So we really need to watch our F words during this unit, field and force. So let's go ahead and put a field on this page where I have this XY axis shown. So here I have a magnetic field. What direction is that field? That field is outward. So this magnetic field points out because you see a bunch of outward symbols with the dot pointing out. Now what we're going to do is we're going to take a charged particle and we're going to send it into this region with a velocity. So let's make our particle a positive particle, pink positive particle. Okay, here we go. Right now you see two vector quantities introduced on the paper. You see a vector quantity, Q, V, where V has a direction and Q's can be positive or minus depending on the type of the particle. The other vector product you see on the paper is B, the magnetic field. When you take the cross product of the QV vector and the B vector, what we get is a force on this positive particle. So as our particle moves into this region, boop, 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 it's going to begin to experience a force. So let's go ahead and at this moment draw the force that the particle will experience. Now, how do you evaluate this cross product to find the force? You can set up a matrix, or you can kind of think about it in a torque way, thinking about rotation, or you may set up your right hand. I have to admit, there has never been a time that I wish this was a left-hand rule more than now. So to set up your right-hand rule, you have F, Q, V, B. It's just going to go in order. 1, 2, 3. F, Q, V, B. Then you're going to make your fingers like you're pointing at somebody, but that all these fingers are broken. So you're not going to tuck them in, you're just going to leave them untucked. Then go ahead and align these quantities with what you see on the page. So our B's are pointing out, so we're going to rotate our hands so our B's are out of this page. Now our QV's need to point to the right. And that will leave our force pointing down towards the bottom of the page. I'll show you in a still frame. Okay, so here's my hand, and it's set up to be used for what's called the right-hand rule. Now we know our QV vector points to the left, so let me rotate my hand to point my QV vector to the left. Okay, my B, which is my fingers, is pointing out of the page. The force will point down on my particle. So I'm going to draw my force in green. So this is the force that my particle experiences, F. Well, what's going to happen sometime later, this particle system is going to try to move forward, but it has a downward force. Moving forward, but being pulled down by that force vector. Now, you'll reevaluate your hand and you'll turn it like this so that your QV vector now points at that same down right angle. See? Down right, down right. Now you realize your force is angled inward at this like that. So we will find our particle sometime later doing something like this. And to set that up, that would make our hand rotate around like this. So now our QV is pointed at that down and left angle, and our force is pointed inward. So this resulting motion will take on a very similar shape because your force product will always be perpendicular to your V. That means that the acceleration that this object is going to undergo, remember force is still ma, is an acceleration that is always perpendicular to the velocity. So let me show you here in the simulation. So here I have an outward magnetic field that gives us the strength. I have a positive charge and a velocity. So let's go ahead and send our particle into the circle. Wow, our particle made that same downward circular motion that we saw in my demo. Now, if you change the charge to be a negative charge, you can predict what might happen. So we'll go in and we could perform that same analysis, making a negative QV. So what would a negative QV vector look like? That would be the same problem here. So to figure out our force on this QV vector in this field, let's make this one blue. What we would actually need to take our fingers and we would point them to the left. So that's how we would set up our hand to match that blue QV. And so at this moment, you realize that the blue charge experiences a force completely opposite to that the pink did. The blue will experience an upward force, while the pink experienced a downward force. So looking at our simulation, what happens when the charge is negative? That same value, negative charge in the field, that same V, went the other way. So if we increase the mass to be a particle with more mass, the object will have more inertia, wanting to continue going as it were going in the beginning. So you'll see a wider circular motion being constructed because the particle has more forward momentum. You can also make the field stronger. So if we make the field stronger, you might predict that the force on that particle will now be more dramatic. So let's take this particle back to its original mass of that first circle right here. And now let's go ahead and increase the magnetic field strength. So the outward arrows get stronger. You can predict what you think will happen to the path that the particle traces out now. Like, whoa, tighter path, stronger force. So let's write out the different aspects of the force equation and see if we can find this dependence on B and M like we see here in the simulation. So let's go ahead and write out the details of force QV and B. So oftentimes we find the force being written as MA, but the A is centripetal because this force is always perpendicular to the V. So then we'll set that equal to QV cross B. Let's take a cross product, a sine of 90. That is perfect 90 degrees, so perfect cross product, QVB. Some people write this out further to say that mv squared over r is equal to QVB. If we isolate the radius in this expression, then we get r equals, let's see, hold on, there we go, mv over QB. So as we predicted in our simulation, when the mass increases, then the radius of curvature of the motion also increases because that object has more momentum. Notice the top term just in itself is momentum, right? And as we saw, when you increased the B, the radius got tighter, the stronger force made a tighter circle. Okay, I'm going to list some practice problems here for you. Go ahead and give them a try, just setting up your right hand. Then I'll show you how they work. Okay, so here I'm going to take my right hand. I'm going to try to get my fingers to align with that B. That B points inward. So I rotate my hand, and now my B's point inward. Oh, but my V is pointing the wrong way. My QV vector needs to point up. Okay, so now I've fixed everything, and I notice my force is to the left. This one's pretty similar to the last one. Get my B's to point in. My QV vector, watch out, that Q is negative. So my QV vector actually has me pointing down, like this, which means my force is now to the right. Here, take your B's and point them to the right. My QVs are nicely pointing upward, and my force is in. All right, so here we're going to have our B's point to the right. Our velocity points into the page, and our force points down. Oh, this one looks spicy. Okay, take my B's and put them down. Now watch out, my QV doesn't match yet. I actually have to turn it this way. And so I realize this is my B pointing down, QV to the right, force is in. For this last one, it's a little different. We know the B's are down. And so we'll put that like this. But we know the force is to the right. So our fingers actually look like this. Our particle, QV vector, is going out. But what direction is the actual velocity of the particle? Well, because it's a negative particle, the actual velocity has to be in.